So this is going to be a recording that explains how to solve some of the different types of problems you're going to approach in this chapter. I'm going to go through each of the problems and show you how to solve them. If at any time you want to stop and try to solve it by yourself, just pause the video, and then when you hit play you can see how I solve the problem. So as we mentioned in class, the first step when you get to a problem is to determine if you're dealing with strong acids and strong bases, or any weak acids and weak bases. So when we look at this problem, we can see we're calculating the volume of 0.034 molar potassium hydroxide. The amount of that's required to neutralize 25.0 milliliters of nitric acid. So potassium hydroxide is a strong base, and nitric acid is a strong acid. So good news here is we have just a strong acid and a strong base, and we're not dealing with any weak acids or weak bases, so no rice tables. So our first step is always to write the overall neutralization reaction and then to write the net ionic reaction. So these would be the overall neutralization reaction and the net ionic reaction for our strong acid, strong base neutralization. You'll notice that we're using single arrows because this is not an equilibrium. The next step is to decide how we're going to solve this problem. And you will notice that we have 1 mole of hydroxide for every 1 mole of H+. And anytime you have a strong acid, strong base neutralization, and it's a 1-to-1 ratio of acid to base, we don't need to do the full stoichiometry problem. We can just use our M1V1 equals M2V2 equation. And because we're talking about neutralization of acids and bases, instead of M1V1 equals M2V2, we're using MAVA equals MBVB. The molarity and volume of our acid has to be equal to the molarity and volume of our base in order for the neutralization to occur. So from here, we just need to plug in our information from our strong base and our strong acid into the equation. We are solving for the value of our strong base, potassium hydroxide, which means we are solving for the volume of our base. So if we rearrange this equation, we have the molarity of our acid times the volume of our acid divided by the molarity of our base. So that would be 0.050 molar nitric acid times the volume of that acid, which is 0.025 liters, divided by the molarity of our strong base, which is 0.034 molar. And when we solve this for our volume of our base, we get 0.0368 liters, which we would always like to report our volume in the same unit that it was given to us. So if we convert this back into milliliters, that is 36.8 milliliters of our potassium hydroxide are needed for this neutralization to occur. So this would be how you solve for the neutralization of a 1-to-1 strong acid, strong base. That's what type of problem this would be. in this next problem, we want to calculate the volume of 0.0045 molar perchloric acid that's required to neutralize 65 milliliters of 0.0072 molar barium hydroxide. So I've identified that I'm solving for the volume of my acid, I'm given the molarity of the acid, I'm given the volume of my base, and I'm given the molarity of my base. Before I begin, I need to write my balanced chemical equation. So when we write this neutralization reaction, we have barium hydroxide, we have perchloric acid. The perchloric acid gives its proton to the hydroxide, and we end up with water and our barium perchlorate. We need to balance it, and what I would like you to notice is that this is no longer a one-to-one problem. We have 2 moles of our perchloric acid for every 1 mole of barium hydroxide, which means we cannot just do MAVA equals MBVB. We need to do a full-blown stoichiometry problem. So you always want to start with a stoichiometry problem with a given measurement. So our measurement here is our 65 milliliters. And we should turn 65 milliliters into liters, so that would be 0.065 liters of barium hydroxide. And we can then use our molarity of our barium hydroxide to convert that into moles of barium hydroxide. So we know our molarity is 0.0072. So there are 0.0072 moles of barium hydroxide per 1 liter. Now we can use our balanced chemical equation to convert from our barium hydroxide, 1 mole of barium hydroxide, for every 2 moles of our perchloric acid. And then finally, now that we've converted to moles of perchloric acid, we're going to use the concentration of the perchloric acid that we have, which is 0.0045 moles of our perchloric acid per 1 liter. So that is some solid solution stoichiometry there. Multiply the top, divide by the bottom, we get 0.208 liters. And we should report our volume in the same unit we were given. So we are going to say that that is 208 milliliters of perchloric acid are needed. So here we have another neutralization. We want to know after we neutralize our acetic acid and our sodium hydroxide, after we mix those two together, we want to know what the pH is. So what we should start off doing, as we always do, is writing our balanced chemical reaction. And anytime you're dealing with a strong, you also want to write a net ionic equation to cancel out those spectator ions. So in this case, our acetic acid, there's no spectator ions there. That does not completely dissociate, so we're going to have some of that left over. Sodium is a spectator ion, so we'll have just our hydroxide, and then on the other side we have acetate. And we have water. So that would be our net ionic equation. So in this problem, we are given the volume and concentration of both of our reactants. In other words, we're given the amount of both of our reactants. So alarm bells should be ringing in your head right now. Anytime you're given the amount of both of your reactants, it is a limiting reactant problem. So we need to figure out how many moles of our acid and how many moles of our base we have, so we can figure out which one is going to be left over after the neutralization has occurred. So for our acetic acid, 0.035 liters times 0.025 moles per 1 liter, we are reacting 0.000875 moles of that acetic acid. And when we do the same thing for the sodium hydroxide, 0.040 liters of sodium hydroxide multiplied by that concentration, 0.030 moles per 1 liter, we get 0.0012 moles of sodium hydroxide. So we can see by looking at these numbers that there is more sodium hydroxide than there is acetic acid. And if we find the difference, 0.0012 minus 0.000875, we see that there are 0.000325 moles excess of sodium hydroxide. When we perform this reaction and we react all of our acetic acid, we're going to be left over with 0.000325 moles of sodium hydroxide. So our ultimate goal here is to find the pH. So now that we know how many excess moles there are of sodium hydroxide, we can find the concentration of the excess sodium hydroxide by using our volume. And we need to remember that we added 35 milliliters and 40 milliliters. So those volumes are additive. So our solution has a new volume of 75 milliliters. So when we take our excess moles of sodium hydroxide, divide by the new volume, 0.075 liters, we find that the concentration of sodium hydroxide in the solution after the neutralization is 0.0043 molar. And because sodium hydroxide is a strong base, that is also our hydroxide ion concentration. So we can use that to solve for our pOH by taking the negative log of 0.0043. And when we do that, we find that the pOH is 2.37, which means the pH is 11.63. This is a very similar problem to the last one, but instead of calculating the pH, we're calculating the concentration of H+. And this time we're mixing 100 milliliters of 0.62 molar hydrofluoric acid with 250 milliliters of 0.248 potassium hydroxide. We're going to want to start out by writing out any relevant reactions that we should be thinking about when we do this problem. And the relevant reaction here is our hydrofluoric acid with our potassium hydroxide forming our potassium fluoride and water. In this problem, we're given both volumes and concentrations of our reactants, so we know the amount of both reactants, which means it's limiting reactant. So we're going to figure out the molar amount, the number of moles that we have of both of our reactants, so we can see which one's limiting and which one is excess. Performing that calculation for hydrofluoric acid gives us 0.062 moles of hydrofluoric acid. And when we do the same thing for our potassium hydroxide, we get 0.062 moles of potassium hydroxide as well, which means we have exactly the amount of potassium hydroxide that we need to react with all of our hydrofluoric acid. It's 1-to-1. We have the same number of moles of each, which means that's a complete neutralization. So now we need to think, we're calculating the H plus in the solution after mixing. It's a solution, there's water involved, and the H plus concentration of pure water is 1 times 10 to the negative 7th. So you're never going to have H plus equals 0. If it's just water, or if everything is neutralized and you're exactly at that neutralization, your H plus is going to be 1 times 10 to the negative 7th. And the last type of problem that I have for you is we're calculating the pH again. After mixing 25 milliliters of 0.25 molar ammonia with 40 milliliters of 0.1 molar, 11 molar hydrochloric acid. We're given the amounts of both, so this is another limiting reactant problem. And we are also given the Kb of ammonia, so that's new, so that probably means we're going to have to do something with that. But I'm going to start off by writing my balanced chemical equation. And I can see from my balanced chemical equation that this is all one-to-one stoichiometry-wise, which is good news. So for my limiting reactant problem, I'm going to calculate the molar amounts of both of my reactants to see which one is limiting and which one is excess. When we multiply molarity times volume for our ammonia, we find that we are starting with 0.00625 moles of ammonia. And when we do the same thing for hydrochloric acid, we get 0.0044 moles of hydrochloric acid. So looking at these two numbers, we see that the ammonia is going to be our excess. And figuring out exactly how much, we find the difference, 0.00625 moles of ammonia are neutralized with 0.44 moles of our HCl. And we're going to have 0.00185 moles excess NH3. And NH3 is a base. We're trying to find the pH. That's a base, but it is a weak base. So if we want to figure out the pH and we have a weak base, we need to know our H plus concentration at the equilibrium, which means we need a Rice table. So I'm going to set up a small Rice table up here. And into this Rice table, we need to put our concentrations. So our initial concentration of ammonia, we're not talking about the 0.25 molar that we started with before the neutralization. We need to use our excess moles and determine what the new concentration is. And when we do that, we take our excess ammonia, we divide by the volume of the entire solution. We get 0.028 molar for our ammonia. That's going to be our initial ammonia amount. That's what's going in our Rice table. And the initial ammonium is 0, and the hydroxide is essentially 0. So in this problem, we don't know any of the equilibrium concentrations, so we are going to have to use x for our change. So we're going to be minus x, and plus x. So we have x, x, and 0.028 minus x. Now we need to use our Kb, which is going to be our hydroxide times our ammonium divided by the ammonia. So we have x squared divided by 0.0028 minus x. We're going to avoid quadratic. We're going to assume that x is much, much less than 1. So we can say that this is x squared divided by 0.002 8, and that's equal to our Kb, and we know that Kb is given in the question is 1.8 times 10 to the negative fifth. And now all we need to do is solve for x. So we do a little algebra, we solve for x, and we get that x equals 7.10 times 10 to the negative fourth. And now we have to think, what is x? X is concentration of hydroxide. So we can use our concentration of our hydroxide to find our POH. So negative log of that number, 7.1 times 10 to the negative fourth, is equal to 3.15, which is our POH, which means pH is equal to 14 minus 3.15, which is 10.85. And you always want to think, does this make sense? That is a high pH, it is above 7, and that makes sense because our excess reactant was a base, so it makes sense that we have a basic solution left over here. So that is the last problem type. This is a neutralization where the excess reactant is a weak component, so we need that Rice table there at the end to then figure out what the pH is. Thanks for watching.